Hi, folks. Welcome to Social Networks and Health. The session today is Positional Analysis for Social Networks and Health. Today, we're going to talk about this notion of positional analysis. Most of the work in social network and health has been done on connectivity. The ways in which things spread through networks has really been a large part of the focus, particularly for peer influence and disease models and such. What we want to do is think about this other side of network analysis, which has to do with the patterns of relations that people are engaged in and how those patterns might give rise to differences in health and health outcomes. We're going to talk through the two main types of this analysis, a centrality model and a block model, and I'll go into those in relatively strong detail with some examples from some of my own work and some others. And then we'll end with some future directions and where things are going from there. Okay. So the first thing to do is to wrap our heads around this first basic distinction between connections versus connectionist effects versus positional effects. A connectionist effect treats the network as a set of pipes that are linked together, and things move through those pipes. So the most common archetypical example would be something like disease diffusion. So one person has the bug, we come into too close a contact with someone else who does not have the bug, and we pass that bug on to them. That connection between them is characterized as a network, and the whole sequence of people who are connected together would be a transmission tree on a network. That's the classic connectionist model. And we're really interested in networks because networks provide a conduit for things to flow through. So it's like wires in electricity or pipes or something, or roads in a transmission network, but it's usually information or disease or resources, something like this is flowing through the network. And the goal is to figure out how people are more or less disadvantaged in that flow system. The positional approach, on the other hand, asks not really what is flowing through the network, but how the different patterns of ties that people are engaged in characterize a role or a role system. And once you have that in place, what comes along with roles and role systems tend to be a series of expectations and behaviors that are also going to be correlated with health. So this notion of a role system has long roots in social science. I'm going back to the early days of structural anthropology, with all of its flaws and so forth. The basic idea there was that there was a structural underlying pattern, and that structural pattern of relations between people characterized social systems, and it was instantiated by the institutionalization of norms as roles. And so a role is something that you do with respect to another person by virtue of your positions with respect to them, right? So, ugly way to say it, but it's intuitive once you know what it is, right? So the idea is that each role has a role complement. Parents have kids, teachers have students, cops have robbers, right? The idea is that there are these things that go together, and we expect people to behave in a certain way given their role in the system. Now, Nadell, in a wonderful old book called The Coherence of Role Systems, argues that it's not just that individual roles exist, that I am a teacher or I'm a husband or I'm a father, right? But instead that these roles intercannulate with other sets of roles to create an entire role system that characterizes a social system. And some of this has roots in old functionalist work coming out of Parsons and such. And so you can leave that baggage behind, but the notion of interconnected roles and the idea that those interconnected roles could be useful for understanding how the social world behaves is really kind of a cool idea. And it's a nice way to think about cross-setting differences, all right? So it might be that one high school is radically different in its smoking behavior than another high school. Well, why might that be? Well, it might be because something like a well-behaved, good student role and a thug role or a rebellious role get conflated in one side but not in the other. So being able to think about the ways in which roles interrelate makes a possibility to explain cross-setting differences as a function of the way these systems put things together. All right. So it turns out then that there are lots of different ways to thinking about this. So in the classic version of role systems, you have these kind of ideas that are thought of as necessary roles, right? And so a necessary role is an analytically required outcome due to the conflation of other things, right? And so kinship is the classic example of a necessary role system. So in a necessary role system, a son-in-law is the conflation of my daughter's husband, right? So that would be a son-in-law. We give it a new name. An aunt is my mother's sister. So you can think about things like that that are necessary outcomes, and kinship is by far the best example. Coincidental things are roles that happen to go together, but they don't necessarily go together, right? So it might be that most businessmen are also members of the country club, and that there's a notion of being a businessman and a political leader are conflated in 1950s cartoons. But it's not the kind of thing that has to be the case. It doesn't have to go together. It just does go together in this case, and we want to take advantage of that and understand the way that works. Right? Now, I've shown this in the intro slides if you managed to watch this, but this is my favorite way of explaining what we do as network scientists with roles and role systems in this idea of position. So imagine I give you a simple network system. It consists of 5 nodes. Those 5 nodes are engaged in 3 types of relations. 2 of the nodes share romantic love with each other, and they feed 3 nodes that bicker with each other. Now, as you might imagine, we don't have to put the labels on these, but we kind of know what they are, right? So these are parents and children. This is an archetypical Ozzie and Harriet kind of family, right? Where you have a world set rife for comedic action in the lexicon of television. But the idea is that we recognize this and understand it because we know what is going on between the actors. And it's the kinds of social exchanges people are engaged in that creates these moments of crystallization about what a consistent pattern of behavior is. So if all I know is that you shared food with someone, that would be inconsistent, right? Because I might feed lots of people that I have no relationship to. If I know that people are bickering with each other, that in itself is not enough to know what it is. But if you add all these relationships together, then that system becomes a role system, and the roles pop out as a function of that kind of setting. All right. Now, informally, right, we tend to think of position in 2 senses. We have a node metric sense, which we refer to as centrality, and we have a collective property sense, which I'm going to refer to by the shorthand of block model here. The node metric sense uses a graph theoretic property of the node to characterize the social position of interest. And it generally treats this as scales rather than categories. And that's probably the main distinction here, right? So you can imagine loners or leaders or bridges, right? Loners are operationalized as people with degree 0. Leaders are operationalized as nodes with a lower network constraint. Bridges are operationalized as nodes with high betweenness, right? Social butterfly is operationalized as a node that flitters between one social relation and another, and it keeps very few of them constantly, right? So you can imagine lots of ways of operationalizing these patterns that we have an intuitive notion for concretely in some metric on the network. And whenever you do that, we tend to call that centrality, which doesn't really mean they're at the middle of the network, right? A social butterfly can be all over the place, but it's just a way of thinking about, it's a shorthand language for the way of thinking about a particular pattern of ties. And we're going to go through in good detail what those things are, right? The block model version of this, or the collective property sense, identifies sets of nodes with equivalent tie patterns to define positions of nodes into classes, right? So it's a partitioning model, just like community detection, but it's different in the sense, in a couple of senses. And so the examples would be that the set of all people who can hire faculty, we call those deans, right? The set of all people descendant from the king, potential heir. That's a small set, right? There's not many of those. There are a lot more deans than there are potential heirs. The set of all female siblings of a father, those are aunts, right? So you get the notion of this is that it's a categorical collection of people that share a relational pattern. And by virtue of sharing that relational pattern, that confers to them some kind of status, obligation, expectation that is instantiated either formally in something like a hierarchy, like hiring for deans or succession for heirs, or informally, right? So part of the big point of this entire exercise is that a lot of roles that emerge in social systems don't have names, right? We practice them, we're consistent, we do what we do every day, but we're not necessarily formally acknowledging that as such, right? And if you can identify that unacknowledged, invisible pattern, it can be really powerful. All right, so positions differ from communities in 2 important ways, right? The main one is adjacency. 2 members of the same community should have a very high probability of being tied to each other. So this is the whole notion of modularity. People who share a position might be in the same community, but they're not necessarily in the same community, right? Similarly, people who are in the same community, so long as it's not a perfect clique, need not share the same position. Some communities will have leaders, some will have fringe members, and so forth, right? So the 2 things are not exactly the same. And the main distinction is this one of adjacency. Positions are a consistent pattern of ties as opposed to a high likelihood of being tied to each other. The second one is a little more subtle, and this is this ability to compound the relation. And this is obvious again in kinship and two-ship relationships, right? So the notion that my brother's kid has a named relation to me that's meaningful as nephew or niece, right? That's a notion of compound relations. Compound relations on communities don't make much sense. So if I'm a member of X and a member of Y, this doesn't work, right? So, but the two-step thing would mean that they're just in a different community, right? So it doesn't work in the same way that it does for positions. All right. So both of these can be useful in thinking about the ways in which networks matter for health. The most common way to do this is that we create variables and we use them in a general linear model. And that's the basic rubric for the way these kinds of things work, is we come up with a measure of the position, and then we ask whether or not that measure is associated with an outcome of interest. Now that raises some obvious issues, clearly some causal ones that I'm not going to get into, but also just some basic estimation and efficiency and bias issues, and I will get into those at the end. All right. So the general kind of way you might think about this, right, is that you'd fit a model like self-rated health is equal to some metric method plus some other stuff that you're interested in. So this is the classic way of dealing with what I'm going to call centrality models, but are all these node metric level centralization things, centrality things, sorry. And here's just a set of examples for the way this works. I think the key thing that I want to point out here is that you shouldn't be limited to just the list on this page, right? I just thought of these off the top of my head. There's a bunch of different ones that are out there that you want to think about. And the whole goal here is to think about the ways in which my engagement with lots of people on lots of relations across different settings creates a unique pattern for me that might constrain or enable health in ways that doesn't otherwise happen. And so that's what some of these examples are, right? So for the cohesion, for example, on the bottom there, you can imagine cohesion as an individual level cohesion set, right? So that's my reciprocity ratio. So the number of times that I name you as a friend, you also name me as a friend. That's a pretty good indicator that I'm a kind of person that's engaged in deep, meaningful relations. You might ask other questions about that kind of relation. And so what's of interest there is not that I'm sharing a lot of information with those people, but having symmetric relations as opposed to asymmetric relations is an indicator of a kind of person, of what the type of friend. I might be a more trustworthy friend or a helpful friend or something like this. And that creates that might be hypothesized to affect the way in which I feel about myself and the way in which others' recognition of me helps me think about myself, right? And that might lead to better mental health or some such. This is the way to think through these processes. And what you want to do is imagine what the sort of probably work from the mechanism. So you probably want to work on this, from the left to the right, or from the right to the left, excuse me, and think about the ways in which something like tight-knit social units, what do? Well, they provide care for people. Well, a way I might operationalize that would be the proportion of friends that overlap, and that I'd call it something like cohesion. So that's just a way of thinking about these ideas. All right. Now, when I say there's lots of ways that you can operationalize patterns on networks, I'm not kidding, right? So there are hundreds, literally hundreds of different published centrality measures in the literature. A lot of them are variants on each other. I love this little graph that David Scott put out that looks at, he calls it the periodic table of centrality. It just classifies as a bunch of them. And it's really just my way of saying, look, this field is huge. And so talking through each centrality measure is not going to be sensible. So instead, we want to think about a handful of archetypical centrality measures and the ways in which they are important. And then think about a set of rubrics for which we can organize all centrality measures. So that's what we're going to do today. Those of you that have had a chance to see the intro slides, I do an entire thing on each of these measures. I'm just putting them up right now here to remind us where we're at. So the classic sort of core four betweenness measures are degree centrality, which is the count of the number of neighbors you're adjacent to. Closeness centrality, which is the inverse of the average distance to every person in the network. So how quickly could I reach everyone in a radiation sort of way? Betweenness centrality is the count of the number of pairs who are connected by geodesics that I could interrupt which is a long way of saying it's the number of times I sit between two other people on the shortest path, usually normalized one way or the other. And then eigenvector centrality. Eigenvector centrality is the extent to it each person is central to the extent that they're connected to other people who are also central. It's a recursive kind of definition that turns out to be perfectly operationalized by eigenvectors. Okay, so each of these are archetypes, and they're good to keep in mind because they do different things, right? So degree centrality is primarily a volume measure. Closeness centrality is primarily a distance, sort of a reaching ability to get across the network kind of measure. Betweenness centrality is largely a bridging kind of model. It captures the extent to which you link different types of worlds. Eigenvector centrality or power centrality are questions about the extent to which the rich get richer and elites are in cahoots with elites, right? So it has these archetypical features that are useful for us. Now, again, this is a deep dive, so I want to go through it in a little bit of detail. Borgatti and Everett really, in a new piece they put together in the Handbook of Social Network Analysis that Ryan Light and I edited, it just came out. They provide a really nice discussion and an overview of the ways in which centrality measures can be thought through. And I want to be really clear what they're doing here. So the idea is that they're not going to give us a formula for a generalized centrality score or something. Instead, what they're saying is there are lots of ways historically that people have justified new centrality measures. And what's happening here is they're trying to collect all those ways to put them into a set of frameworks to help us think about positions. And so I think it's a really valuable approach that they've done here, right? So the three measures they give, or the three frameworks, excuse me, they give, are this walk structure participation perspective, which organizes centrality by the pattern of walks and paths in the definition. And I'm going to go through that in a minute. There's an induced centrality perspective, which says centralities matter because of what they do to the overall network structure. It captures the extent to which a node contributes to some graph level property. And then there's a flow outcomes perspective, which focuses on the way in which a node affects propagation processes through the network. Now, most of these common centrality measures can be discussed from each of these perspectives, with the exception of a few weird things. But basically, these are different lenses through which to see all of the centrality measures we typically talk about. So the walk structure perspective is probably the original one and the most common, because what it's really doing is just pulling us straight out of graph theory. And so what it's saying is, let's imagine graph theoretic properties on a network. So a network is a series of nodes and edges. And then ask, well, what are motifs or patterns on those nodes and edges? And the way you do this is you think about paths, trails, and walks. And so a geodesic distance is, again, to go back to the first set of lectures, we go through these definitions there. But the idea is that you can think about the kind of traversal, which is the way you move through the network. If you start at one node, you can take an edge and get to the next node, go to the next node, and so forth. A geodesic is the shortest possible path amongst all paths, all possible routes that you could get from A to B. A path is any sequence of nodes and edges that get you from A to B that never goes backwards. All right? A trail does the same kind of thing, but it doesn't go backwards either. What's the difference between a path and a trail? I'm drawing a blank here. Sorry about that. And a walk is random. A walk goes both ways. All right. Hey, folks, sorry for that. Yeah, so the difference is a trail is a walk that doesn't repeat on edges, but it might repeat on nodes, right? Whereas a walk is any sort of random bouncing around through the network. Apologies for that brief brain fart. All right. And so then the question, so you have the way in which things move through the network. So a geodesic, for example, is aiming to get the shortest route. And so it's a shortest possible distance. And so it's very search oriented. And then the second one is the position in the traversal. So is the centrality measure characterized by being at the start of this, in the middle of it, or at the end, right? So are you something that you're either an endpoint, in which case you're receiving lots of flow or sending lots of flow, something like that, or in the middle, can you break it up? And then the question about the what are you counting on this traversal? Are you counting the length of it, so how many hops it takes, or the number of times you pass over a node or something like that? So for example, degree is a frequency measure, right? So the property they're measuring is the frequency, of the endpoint on a geodesic of length 1, right? So that's what a degree is. So it's the count of the number of one-step paths you have to other people. Closeness is a length feature characterized by the endpoint on geodesics. Betweenness is a frequency measure based on the being in the interior or mediating a geodesic. Eigenvector is an interaction term between the length and the frequency of walks as an endpoint, right? So this is the idea that you can sort each measure into this set of rubrics. And that's great if you're a mathematician or a graph theorist and you want to think about some arcane properties and how they might fit. This is the table they give in the paper. It's a nice discussion of these kinds of things, and it shows, I think what's nice about it is that a lot of these kinds of things we don't use, right? So common measures that we often use, like degree centrality, for example, or betweenness centrality, these things tend to work on geodesics. There's some historical reasons for that because of when the algorithms were invented and the ways in which they work quickly. But a lot of the measures that we have, the common measures we have, don't neatly fit into some of these properties. Now, it's a little bit backwards, as you will see here in a second, to think about it, but you could imagine just thinking about, well, what would be a length measure on trails? That would probably be kind of fun because of the fact that trails use are walks that might meet the same node multiple times, but never the same edge. You could be thinking a way of getting at recurrent connectivity, right? I don't know, I just made that up literally on the fly, but it's the kind of thing that you might want to think through as you go, if you're trying to think through a social mechanism or something. Generally, I find that it's better to go for the other directions, to start from the social process and work back to the graph theoretic measures, but it's a nice rubric to put everything in. Okay. So the second idea, which I think is really nice, is this idea of an induced centrality perspective. And it said a node is as important to the network as its removal would be consequential. And that's, I think, probably the single best way to capture the ways in which a node, or possibly a set of nodes, contribute to this entire massive system, right? So what's a little bit like both fascinating and frustrating about networks is that they are this entire huge connected system. And what we typically do with the walks and trails kinds of models are say, well, let's find one specific property of that node and measure that for all nodes. And so they're nice and clear in that sense, but you don't know what it does to anything else. And so what's nice about the induced centrality perspective is that there are easier ways to calculate it, but intellectually what you do is you calculate some statistic for the graph, some graph invariant, like centralization or overall connectivity or something. You remove that node, calculate it again, and see how it changed, and that change score is due to the connections that node provides to the network. So it really is this residualizing process of removal of a node on the network. And it's great for things like diffusion. So if you wanted to know, for example, the likelihood that a node was contributing to the susceptibility of disease flow in a setting, see how fast the disease would flow without that node, right? And so it provides you a way of thinking about the contributions that a node can make to the overall set. What's also important to this is that you can say, well, what are the pair of nodes that if I removed them would have the greatest effect? Which you would think it might be the first node with the highest set and the second node with the highest set, but that's not always the case. It's often the case that nodes that in combination can do things that either of them can't do. And that's part of the magic of emergent properties with networks. So there really is a clever way to think about this. Borgatti has a whole field around what he calls key player analysis that uses this residual graph idea to think about identifying nodes that are key players for either bridging or disconnection or influence or so forth and so on. So it's a nice way of thinking about things. The final version that they give is this notion of flow outcomes perspective. And here's where you see a little bit of the blurring of the lines between the connectionist approach and the positional approach. And lots of things that happen as centrality measures could be characterized as the ways in which something is getting passed around the network. And if you think about the different ways that things get passed through a population, it turns out that each of those ways that things get passed through a population can be operationalized on a graph. And so it might be a good idea that if your goal is to think about the way that something spreads, like information or rumors or good health behavior or disease, that it's characterized by certain patterns, right? So viruses they don't necessarily take a geodesic, right? They just sort of move off to the next adjacent node. So they do gauge paths, but once you've been infected, you're unlikely to be reinfected by the same virus, at least in short order. So it never goes backwards again, right? So you don't get this kind of walk or trail idea. Instead, it's always spreading out. And moreover, it's being copied, right? So I have the virus. When I give it to you, I still have some left to give to the next person, right? And so it's a copy replication as opposed to a transfer, right? Whereas if it's a used book, once I've read it and hand it to you, I can't then hand it to somebody else because there's only one copy of the book. So it's a nice way to think about the way resources can flow through networks. And what you do then is you tie these notions back to the centrality ideas. And they give a couple of examples of this in some of their other work as well. So it's the whole point of this is to think about the ways in which different centrality measures can be thought of as capturing patterns on networks. Now, I also like to say, and just to point out, that most of the time thinking about a single centrality measure is probably not sufficient. If you really want to characterize a position in the network, it's often the unique combination of multiple centrality measures. And again, this is a slide replicated from the first days of slides. But the idea here is that if you have high betweenness, say, and low degree, that means that I have a very small number of ties, but those ties are going to reach lots of people. So this node is very likely to be a cut point in the network, and it operates a really key bridging node. Whereas someone who has low betweenness and high degree, sort of in the opposite corner over there, this means that a person is engaged in lots of ties, they're really active, but they're not very essential for global spread or something like this. And so again, once you have this notion of combinations of centrality measures, you can really sort of hone in on unique positions within the network. Now, the second way of approaching the positional analysis model is to focus on these classes of nodes. And this goes back to the little kinship example we gave before. The idea is that we start with a basic idea of what a role is, and we try to induce that from the patterns of relations. And this is, at the end of the day, a partitioning exercise. We're going to sort nodes into classes. All right, and so how do you do that? The basic way to do this involves 4 steps. You have to identify some definition of equivalence, and then we're going to spend a good deal talking about that. We then measure the degree to which pairs of actors are equivalent. And so this is a dyadic analysis in that sense. And then we develop some representation, either as an image matrix or a dendrogram or something to capture the extent to which people are similar to each other. And then we ideally test the fit, sort of assess the adequacy of the representation. Now, some of these are not all done simultaneously, but at the end of the day, this is community detection on a role equivalent similarity matrix rather than an adjacency matrix. So that's the other way to think about this. If you've already taken Peter's course in this sequence and have learned all the best new tricks on how to do community detection, think about applying community detection not to the adjacency matrix, but to a role similarity matrix and your home free. Okay, so equivalent with respect to what is the question. So the first thing to keep in mind is that we're often interested in these kinds of models for thinking about relational systems. And because it's relational systems, we're actually thinking about multiple relational necks or multiplex relationships. What that means is that we need some way to characterize the similarity of nodes with respect to all relations simultaneously. And this is something that centrality scores don't do particularly well. You can get a centrality in the eating network, a centrality in the feeding network, and a centrality in the romantic love network, say, but the sum of those 3 scores is not going to be the same as the similarity across all the scores. So it's probably the best way, I think, to deal with these multi-relational systems is to think about them in terms of these role similarities. And so the classic way to do this is that you take each relation separately and you stack it. And so in this case, I've taken the romance adjacency matrix, the feeding adjacency matrix, and the bicker adjacency matrix, and I've stacked them over here into a 4 by 5, so 3 relations with 1 repeated super matrix, if you will. And then I go through and I just count the extent to which column 1 is similar to column 2, column 1 is similar to column 3, column 1 is similar to column 4, and so forth, and I can get a similarity matrix out of that. Now, in this case, because it is a toy example, the similarities are perfect. Parents are similar to each other, children are similar to each other, and they're completely dissimilar to each other. You'll probably, those of you that are paying attention will probably notice that I did put a little trick here, and I took this matrix, the feeds matrix, and I flipped it. And so you have both the who feeds and who is fed matrix put on top of each other. And this is how you deal with directed relations. So that helps you figure out who's similar with respect to both sending and receiving, because the two might not necessarily correlate as they do in this example. Does that make sense? Hopefully it does. I'm used to asking questions. This is the problem with recording. So, all right. Sorry about that. So it turns out there are a handful of different equivalence measures. The classic in the field, and when we talk loosely about it, people just refer to it as structural equivalence as the general term we're talking about. But technically, structural equivalence is the most constrained form of equivalence. It says that two nodes are structurally equivalent if they share the exact same ties to the exact same people, right? So the only thing that differs between two nodes that are perfectly structurally equivalent is the label on the node, right? And these are pretty rare, right? So finding actual true structurally equivalent nodes tends not to happen in most social networks. The one place you will see it a lot is when you have hub and spoke networks. So airline networks, essentially every pendant going to a hub is equivalent. They're all little end branches at the end, and the connectivity structure is really driven by relationships amongst the hubs, right? So if you think about what this is, it really is a very constrained notion of two nodes having to be literally substitutable in the adjacency matrix. Automorphic equivalence relaxes that a little bit, and it says that it's the same pattern of ties to all others in the network, and nodes are indistinguishable on any summary statistic, right? So the idea here is that you and I might not be tied to the same people, but we have the same pattern of ties to the same people, right? So in the structural equivalence example, two pendants of the same hub would be structurally equivalent. In automorphic equivalence, two pendants to any hub would be automorphically equivalent. Now, relaxing that one step further is a notion of regular equivalence. In regular equivalence, you have the same types of ties to similar types of people. And so what the idea here is to try to capture this notion that, brothers are related to aunts in the same way, whether you have 4 aunts or 2 aunts, right? And so it shouldn't matter that you have a lot of them or few of them. What matters is their characteristics and their patterns of ties. Operationalizing this is a little bit difficult. Substantively, it's the same types of ties to similar types of people. And so it's nurses to doctors, managers to vice presidents, and so forth. But operationalize it ends up being a little bit complicated. And I'll show you how we get to that in a second. It ends up being that a lot of these fine distinctions get washed out once we get to operationalization, because an imperfect operationalization of structural equivalence is probably going to give you automorphic equivalence, and an imperfect operationalization of automorphic equivalence will probably give you regular equivalence. So if you think about it, it's useful to know a little bit about these types of things, but it's not necessary to have an exact example, right, to get your work done. Here's an example. I'm just on a toy piece to illustrate what we're talking about. In this case, we have a very simple little network here. You can tell it kind of looks like a hierarchy. And I've lined out the blocks that are perfectly structurally equivalent. And I just want to make clear what that is. And so you can see, you might say, well, these two, A and B, are both at the top of the hierarchy. They must be equivalent. And it turns out they are automorphically equivalent, but they're not structurally equivalent because they send and receive from different people, right? So you can see over here that person 1 sends to persons 3 and 4, persons 2 sends to persons 5 and 6, right? And so that creates a difference. Whereas C and D and E and F, these next two little blocks, they're the same patterns of people, but they're assigned to different folks. And so that's what structural equivalence is. Now, the way that we find operationalized structural equivalence originally, this was White, Borman, and Breiger. They used an algorithm called CONCOR, which is the convergence of iterated correlations. It's not used much anymore, which I actually think is probably too bad. There's some goodness to it. It was pretty effective at getting some things done, but it's worthwhile to walk through it and get an idea, because it's a pretty clever little algorithm. So what happens is you can just operationalize this idea of similarity directly by the correlation. So I replace the adjacency matrix with the correlation of column 1 to column 2 probably, if it's directed relationship, stacked on top of row 1 to row 2, right? So you could, if it's directed, you do it here, we don't have to. But you just take so we replace their adjacency with their correlation with respect to all other nodes in the network. And so we can see then that this is what that correlation matrix looks like. And so here you see that the nodes that are structurally equivalent will have perfect correlations inside their block. And that's in fact the definition. And so you can see why this is an intuitive way to do it. And then we want to say, well, what makes them similar? This is often too fine-grained, and so can we roll it up a little bit? Well, it turns out that I can say, well, how similar are you with respect to the similarity matrix, right? So I do the exact same thing again. I just take the first column 1 and I correlate it with column 2, column 1, I correlate it with column 3, and now I'm taking the correlation of the correlations and I just do that over again. So I do it again. So here's the first iteration, second iteration, third iteration. You'll notice this almost immediately, right, converge to either all positive ones or all negative ones. And this is an inherent feature of correlation matrices. If you engage in this multiple correlation process, you will get this kind of an outcome. And there are some deep roots in this in principal component analysis and SVD that we're not going to go into, but I think it's a nice sort of, it's a feature they were able to pull out of this function. So now you have this matrix of positive ones and negative ones. If you just reorder it, you get your first cut on blocks. And that's the way that Concore works. And you'll see in this case, we have nodes 1, 3, 4, 7, and 10, 2, 5. These end up being both branches of that hierarchy I showed you up above, right? So this is, this is one branch, that's another branch. And so the first cut on this one was selecting out on that set. Now, if you think about the way this plays out, the way it works is you then take your first cut, your first block, you would take nodes 1 through 1, 3, 4, 7, 8, 9, and 10 here, pull those out and repeat this process just inside that block. And there's some there's different versions of the algorithm, whether or not you include ties to people outside the block or not. Most of the time you do, unless for scale issues you can't, but that's down in the weeds. And then you split it again, and you just keep splitting until you get a fit that is sensible, right? And this is a part that's a little bit hard for people to get because everyone so wants a stopping rule. The official stopping rule is to have you decide whether you have fat blocks or empty blocks. That is, do you have all ones in a block or all zeros in a block? And if it's mixed, then clearly you haven't found structural equivalence yet. That's true, but that ends up creating a solution that's way too fine in most real-life cases to be useful. So instead, what you do is you examine the hierarchy splits like you would for most cluster analysis and try to figure out a spot that is effective and informative. And in that sense, these kinds of models can have a pretty qualitative sense to them. You need to explain why you made your stopping rule, but the stopping rule tends to be one of user judgment. Okay. Let me give you a little example of how Concore has been used successfully. Peter Muka and I had this crazy idea that we wanted to model Senate co-voting networks. And it turns out that the problem with Senate co-voting networks is they're really, really dense. And so most of the blocking algorithms you do are kind of silly because you just get Democrats and Republicans, and you don't get any kind of variation between Democrats and Republicans. And believe it or not, there used to be a day when the divisions between Democrats and Republicans will always dominate, were never completely determinative. And so what we did is said, well, let's characterize the Senate not by the extent to which you have ties just to your party or not, but by the pattern of ties you have, and let's identify structurally equivalent nodes. And so this is a one session of Congress, when temporal session, all the positive votes, you're connected if you voted together, you're disconnected if you didn't. And it turns out that in this particular year, you get a handful of different positions. And so you always see what we're going to call party loyalists of one sort or the other. But there's a fair number in this session of people who are crossing the aisles on particular kinds of issues. And that's what makes them distinct from each other. So this little green node here isn't connected to this node because while they both vote outside their party, they don't vote outside their party on the same thing on the same times, right? And so that creates a structural division about what they care for. And I don't remember the example. It might be that one is more interested in, agricultural issues and one is more interested in poverty or policing or something. But whatever it is, it signals a difference based on this similarity set. So then we went through and just coded it by the extent to which they are similar or different. Okay. The nice thing about this process is if you do it, you can do it over and over and over again, and you get something like this. So in this case, each of these little circles represents a structurally equivalent position in the network, with Democratic Party loyalists on the top, Republican Party loyalists on the bottom, and then lots of different variants in the middle of the ways in which you can be a between party actor. And this ended in 2012, so 10 years ago now. And so I'd hate to see what it looks like now, but you can see back in the early 90s when the system first started to crack into its modern polarized sense. Now, it turns out that block modeling by Concore is a bit out of fashion. People are using other methods now. And so one of the methods that I really like is one that's been created by Ron Burt in a paper he wrote in the 90s on detecting role equivalence that builds off triads and triadic analysis. And it's a way of operationalizing role equivalence. And the way to get your head around this is to think about what triads actually capture, right? So triads I always refer to as the periodic table of social elements. These are the basic things that get us out of what Zimmel called the dyad into a supra-individual group, which is a triad. And the ways in which I relate to all other folks in a triad really does characterize my full pattern of relations to everyone else. And so we can see here, right, that these are the patterns that capture a friend of a friend is a friend. These are the patterns that capture hierarchical agreement that we think we all agree on who's a hierarchy. These are the patterns that capture reciprocity. And so you can imagine then, once you disaggregate these, that people who have a similar set of patterns are going to be involved in a similar set of triads. And that's the intuition behind this method. So you can decompose any network into its constituent set of triads, and you can count those. You can, once you do that, you can see that the triad distribution also characterizes not just an individual's involvement, but what the system itself is constrained to look like. So if you have some kind of a cartoon world in which you have only O3OT triads, only this triad right here, where A dominates B, B dominates C, and A dominates C, right? If that's the only triad you have, then your macro structure must look like a perfect linear hierarchy, as nothing else is possible. And so what I'm trying to hint at here, and then there are a bunch of these kinds of models, you can see them in the slides. Eugene Johnson has some wonderful papers on these, is that the triads you're involved in characterizes not only your role, but in the classic Nadel sense, the role system overall. So it really does a nice job of capturing all of that. So to operationalize that, we have to go into the triads, and we have to ask how each person is acting relative to every other position in the network. So if you take ego, as indicated by the square, in this triad, which is an ego, there's one node sends to another node, and the third person is unrelated, right? So this is a single arc triad. There are three possible positions inside this triad. You can be the sender, you can be the receiver, or you can be the bystander, right? Similarly, in this one, because it's reciprocal, the sender and the receiver are the same, the bystander is out here by itself, right? In this case, you get a sender, you get a person who's between, and you get an endpoint. And so you get the idea. It turns out on the 16 directed triads in a network, there are 36 positions that can be identified. And we can just count the number of times you're in each of those 36 positions. And this is, I've just done this for a little example graph. Let me move my mug out of the way. Right, so you can see here that there are, as for all networks, because if they're of any size, any three people are going to be disconnected from each other. You get a large count of, this is the count of number of times you're engaged in the empty triad. This is the number of times you're a member of the dyad. This is the number of times you're a member of the bystander, and so forth, right? So once you have that, you just calculate this node similarity across each of these sets. And you'll see in this case now that A and B are put in the same set, C, D, E, and F are put in the same set, and these guys are put in the same set. So it really does pull out what our intuition would say the roles are in this network. And we end up with a situation that looks something like this. We can play out this example. We've myself and a few others have worked on these problems with a data set called the Prosper data set. The Prosper data set has about 368 different schools, and this is just one small 6th grade classroom. And this is what the relationships look like, right? So symmetric relationships are in this orange color, and directed relationships are the black with the arrows in the heads. I go through and I calculate this kind of position for each kid in the school, right? And then figure out at what point in I run a clustering analysis on the resulting similarity matrix. And then I just do a modularity maximization search through this to identify the spot where to cut the network. And so in this particular school, this is the positions that end up. If you roll up each of those colors into a single position and looked at the pattern of ties to and from each position, you get something that looks like this, right? So you get one group, we're going to call this cluster 7, and cluster 7 has lots of ties to itself, and everyone else likes them. Cluster 3, they don't tie to themselves more than you'd expect by chance, but they all pine after cluster 7. Cluster 6 recognizes itself, but also pines after cluster 7, and cluster 7 sends back a little bit of love, but not as much love as they get, right? So this is a classic lieutenants or hangers-on kind of position. These groups recognize each other as outsiders and have a weak connection to the center, and these folks are outside entirely. The difference between 1 and 2 is pure isolate versus some internal connection that's not enough to get beyond chance. And that's something that if I hadn't automated this, if I had done it by hand, I might have merged groups 1 and 2, but I made that trade-off for repetition issues. Now, if you read the big data, if you go to look at the big data slide deck that we have up as well, I'll talk through this whole process, but essentially we came up with a method for clustering clusters in order to replicate this on all 368 networks. The end result is you end up with a lot of different positions that are characterized by their involvement in positions. And I'm just going to jump to the conclusion on this one as opposed to the way we got here. To walk you through the kind of positions we involved and how these things work, right? You can see that if you go down our cluster hierarchy here, this is our cluster of clusters hierarchy. This branch is represented by these 3 clusters at the end, excuse me. And here you have essentially your outsiders, right? So you have cluster 1 out here. These are the folks that their dominant triadic configuration, there are 36 bars here if you want to take a moment to count them, right, is being involved in this one. They're the bystander in this triad. And what that means is these are folks that are largely isolated. And if you look at the other sort of ways you could capture their position in the network, they tend to be lower than we would expect at average for every kind of thing out there, including out degree, transitivity, and everything else, right? The popular loners, on the other hand, these are folks that every once in a while they get a tie from some other people. And so you can see they're involved in a slightly different signature of triads. That's what, again, 1 through 36. And their pattern is largely negative like the others, but they have a higher, they don't have this huge distinction between out degree and in degree. And they are receiving a few more ties than they might otherwise. On the other hand, if we think about this hangers-on group, their main characteristic is they are sending ties to people who don't recognize them. All right, so these are folks that are sending lots of out ties, but not receiving many ties. And you can see that here in that they have a strong negative in degree and reciprocity, but positive in the others. So they're sending to the right people, like so they're saying they're friends with popular people, that those people aren't responding in turn. If you go through the slides, you'll see there are a bunch of these ones. We can characterize the leading crowd. Here on the other branch, I didn't put the branch hierarchy up here for some reason. But these are groups that are overly involved in the really dense hierarchies, particularly as receivers. So you see this particularly high in degree, but also very high power and closeness centrality. And that's in contrast to the aloof elites. These are the people who are kind of there, but not really on the inside. These folks are receiving lots of ties, but they never make ties out. They don't bother to send ties to other people. So this is the idea of the way in which a positional analysis can work for clusters on ego networks. And you can see then that the next step in this process is to name it. And after thinking about this for a while, we assigned them names based on essentially a tripartite breakdown of their patterns of ties that had to do with their involvement in the hierarchy, the reciprocity they were involved with locally, and the amount of activity they were engaged in totally. And so you can see then that each of these clusters maps on to one of the others, right? And so our leading crowd cluster, like these are folks that are higher in hierarchy, high on reciprocity, and high in volume. And that's distinct from our aloofs that are, again, high on hierarchy, but they're low on reciprocity. And that's how they end up in that spot. Right? There's a lot of outcomes that tend to matter for these folks. And so you find, for example, that they differ in the extent to which men and women are engaged in them. They differ in the extent to which poor kids, these are ranked roughly between the high centrality kids and the low centrality kids, just to give some sense of order. And so poor kids tend to be out here in the outsiders, loners kind of group, whereas rich kids are more likely to be in the leading crowd. Or in the leading aloofs, particularly. Notice, of course, that there's a lot of variance between schools, so these means are, only somewhat informative. And it also was fun to think about it because this is a dynamic network. Once we've defined these positions as a consistent pattern across the networks, we can ask questions about how they stabilize and change over time. And what we find, for example, is that in 6th grade, there's lots of movement between, this is a mobility matrix now, there's lots of movement amongst the positions. Kind of block diagonal, right? So you kind of get a popular movement up here in the Federated Friends leading crowd kind of set, and some movement amongst the outsiders. So you get movements in this cluster, movements in this cluster, but there's a little bit of movement back and forth between, which you can see in this set. And then as time goes on, as you get up to our last set here, these positions have really solidified. So by the time you get into junior high, 9th, 10th grade, it ends up being the case that your probability of moving from one position to very far is really low, and most people stay roughly where they are. We can flip this. We can ask what happens at the individual level, right? And it's kind of fun because we can say what kinds of people are likely to move between one position and the next, controlling for all the other things you might expect, like the time and wave and such. And we find that women who started in the leading crowd are more likely to move into something like the aloofs, and very unlikely to move into these cases over here. Sorry, the red is unlikely. So if you're a female and you're a member of the leading crowd, you're probably going to stay there. You're very unlikely to move. If, on the other hand, you're in any of these positions, right, you're more likely to become in the Federated Friends. So outsiders, if they're going to move anywhere, this is relative to staying in the diagonal, they're more likely to move to this Federated Friends, which would represent sending ties to people that aren't recognizing you, right? So these are people that you tend not to stay there very long. It's an uncomfortable position. You want to go somewhere, and they tend to go into lots of other places. And we have a whole bunch of these ideas that you can go through there if you want to, if you're interested in it. I want to stop there for a moment. All right, so as a way of thinking then about some of these processes, the second way of thinking about these models is that, again, I like the triad model because it captures what triads are good at. And what triads are good at are capturing sort of detailed local patterns. Triads are a little expensive to calculate. They're not as bad as they used to be. We've gotten pretty good at it, and the algorithms are fine. But the whole point of automorphic equivalent, it turns out, is that nodes are indistinguishable on any summary statistic, right? And so the best strategy, if you don't want to go through the trouble of calculating all the triad types, or you want to look at multiple relational networks where the number of triad types explodes combinatorically unreasonably, then you can calculate bunches of summary measures on networks, any kind of node metrics that you have the time and energy to calculate. Ideally, they're informed by your theory to some degree, but honestly, they don't have to be. The goal is to just find nodes with the same pattern. Then you can calculate that as a vector, and then look at that vector and ask, well, how similar are two nodes on the vector? John Morgan and I were engaged in a project that was looking at a network that had over 4.5 million nodes in it, right? So big, giant networks. And this was our solution to identifying roles in that kind of a setting, which is that we calculated a bunch of statistics on the node that had to do with your involvement in your local community versus bridging to other communities, because the theory we were engaged with had to do with the ability of nodes to be key players in the system, right? And so when we did that, we ended up generating something like 15 different metrics that we measured up, we felt were relevant to this question. and this kind of pattern question. And then we just use cluster analysis on those 15, on that metric space, a 15-dimensional metric space, to identify a subset of nodes that have the same kind of pattern. And what we ended up finding is that essentially there are, ended up being a hub and spoke system, and you had rows 7, 8, and 9 here are your hubs, these 7, 8, and 9, and these end up being nodes that have a very different pattern to what are otherwise sundry sorts of pendants over here in rows 1 through 3, or different kinds of active internal members. And the differences, if you're interested, the differences tended to largely turn on the kind of tweet they were involved with, so retweet versus comment, that kind of stuff. All right, so there is a little, what's the phrase? Little niggling concern that people might have at the back, which is that we spent all this time talking about how you construct a network equivalence measure and how you might use a positional measure to predict an outcome, or ask how people's position in the network is a function of their health outcomes or some such, right? But anytime you collect a measure on a network, you run into this problem that the measure itself must be correlated with other things in the network. That is, by definition, your observations are not independent. And that violates the core first assumption that we've all been taught of our statistical models. And so what do you do about that? The main substantive trick we're going to try to do is model an health outcome as a function of a network position score, either a membership factor or a centrality metric. Once we have that, then can we trust the results we get out of it? Now, there are a couple of ways of thinking about this, and I'm going to tell you up front that the literature on this is a little unclear, so I think there's a good deal of work yet to be done on this. And Jeff Smith, John Morgan, and I are engaged in a big Monte Carlo simulation project to do just this work. But the two modes of thought are that on the one hand, by virtue of asking a positional question, you have captured whatever pattern issue is engaged in the network that would create autocorrelated errors. And so that's actually going to mean that you have conditional on that metric. There's nothing left over. You've actually captured a good deal of the thing that would cause problems if you were to otherwise use the data and ignore it. And I'm sympathetic to that model, particularly if you've used one of the categorical versions of automorphic equivalence or something like this. There are very few things left in the network that you couldn't have wouldn't be captured in that positional analysis. If you're using something a little more unidimensional, like a centrality score, then you might still have a fair amount of network autocorrelation. And so just to give you an idea of what this looks like, you can imagine if you just run a little model where you, with a known outcome, and this is a simulation result here, where we say, let's simulate the network data, and then in fact, I used real network data, but let's simulate the association between some made up outcome, we're just gonna call it Y, and information centrality. I'm gonna do it under two regimes, one where there is autocorrelation and one where there's no autocorrelation based on the peer influence of the errors. That is, that my error is related to your error, and that's what this little other stuff would be, right? Now, if you do that, it turns out that a regression model will almost always give you an unbiased estimate. Now, that's the good news, right? So the good news is that you end up with a somewhat wider distribution of the estimates, right? So it's not the most efficient estimator, but like all correlations, it doesn't lead to autocorrelations. It doesn't lead to a biased outcome, assuming that it's just in the error that you have this outcome. But unfortunately, if you look at the standard errors for those estimates, right, the true standard error is here. Your observed standard error with the autocorrelation is almost always lower than it is in the true case. So that means you're overestimating the significance of your results. That's the bad part. So you're getting the right estimate of the value, but the wrong estimate of the significance. And in fact, you're probably overestimating the significance because you're underestimating the standard errors. So you can fix this, right? So the classic way to fix this is to use a spatial autocorrelation model and to actually ask the model to tell you whether or not there is any autocorrelation in the network. And so if you do that, it ends up that you still get a an unbiased estimate, so it doesn't change the estimate at all, but it does change the standard error for the estimate. So in this case, then you end up with standard errors that are actually a little bit higher, so your significance test will be a little bit more conservative if you do it this way. So that's my recommendation, is to find some way to account for the errors that might be there in your model. And the simplest way to do it is to use a standard network autocorrelation correction. Excuse me. All right, so let's sum up a bit now. All right, so to sum up then, positional analysis is a much less common approach taken in network analysis and health. I think it's ripe for exploitation, right? There's lots of things you can do with positional models that haven't been done yet, so I strongly encourage you to do that. It turns out that we have lots of tools to do this. We just haven't been thinking this way that much. The thinking on positional analysis, I think, has tended to be that almost completely driven by peer effects. The main driver in networks and health have either been peer effects or diffusion of disease. And this notion of position has just been kind of neglected. And so I strongly encourage you to go out and think this way, because the tools are now ripe for making this work. We have more centrality measures than we know what to do with, and they can now be mapped quite clearly by virtue of these different rubrics to social mechanisms. And by thinking about the social mechanisms, we can think about the ways in which involvement in networks affects your health, in addition to the kinds of resources you might draw and information you might draw from your networks. The one thing that's left in these models, particularly for the classification versions, are that these still require a fair amount of investigator judgment. I consider this a feature, not a bug, right? I think that science is better when people are engaged with it and not just following blind rules. So I think that's okay. The key element is just to make sure you write down what you did and why you did it, and are indicating when you're making a choice that could be substantive, like whether I have 6 clusters or 7 clusters, something like this. Like, these kinds of choices are analytic choices based on your judgment. That's just the nature of the beast. It's a good thing, I think, so long as you're engaging your judgment as opposed to just trying to follow a rule. There are some concerns over models' independence, right? So the estimates of these models are going to be a bit tricky if there is unobserved error that you can't account for. For the most part, you can account for these kinds of errors in the standard ways you deal with autocorrelation, which is either to model it directly with a network autocorrelation model, for which there are easy ways to do that, to hijack spatial autocorrelation packages, for example, or to include other variables that, once you've included them, makes the network effects, the error effects, conditionally independent. And so I think tests for unobserved autocorrelation can be helpful, and we're developing some of those as we speak. So thank you for paying attention. This went a little longer than I'd hoped it did. And so for those of you who made it to the end, congratulations. And please do send questions or comments to us on the list so that we can have an engaged discussion on this on Friday. Talk to you all soon. Bye.